recording here. And yep, we're good to go. Floor's yours.
Thank you, Carter, for that wonderful introduction. Hi, my name is Akul Goyal, and I'm going to present my paper, You Aren't What You Do, Mimicry Attacks Against Provenance Graph Host Intrusion Detection Systems. This is joint work with Adam Bates and Gang Wang from UIUC and Michael Hahn from Wake Forest. So host intrusion detection is a canonical security challenge dating at least as far back as the 1972 Computer Security Technology and Planning Study. Even the seminal Multics project boasted its own host intrusion detection system, or HIDS, that came equipped with its own security dashboard. Unfortunately, since their inception, HIDS haven't really exhibited resilience to adaptive attackers that deliberately attempt to evade detection. Consider the canonical example of the Forest IDS. During training, Forest IDS builds a database of normal system behaviors by moving a sliding window of the system calls of an audit event stream. The size of the window dictates how the event stream is decomposed and represented in the database. During testing, Forest IDS then compares the event stream to a database of known behaviors. An alert is raised if any tuple in the system cannot be found in the database. With this schema, it may appear rudimentary. Its approach to system call analysis is fundamentally analogous to many of the HIDS technologies used today. Wagner and Soto were the first to observe that an adaptive attacker could mimic the database of normal behaviors in order to avoid detection while still accomplishing their objectives on the system. For example, let's imagine that the attacker's objective requires them to issue an open syscall, then a read syscall, then a write syscall. Notice that this behavior is not existing within the normal database. If the attacker is in control of their own malicious process base and possesses knowledge of the normal system activities, they can exert arbitrary control over their system call sequences by injecting chaff benign events into the event stream, causing each tuple to match those in the database. It is also worth noting that this event stream looks nothing like the training data from the previous slide, but still evaluates as normal. This is a result of the minimal foreign sequence problem. The parameter used by Forest IDS to create a digestible representation limits its visibility of attacks. So recent advancements in machine learning and system auditing have caused researchers to consider intrusion detection as a graph learning problem. Pictured here is a provenance graph of normal system behaviors from the DARPA Transport Compute dataset. Ovals denote processes, rectangles files, and diamonds network addresses. Edges denote the system call relationships through which these system entities interact. Provenance graphs are a parsed representation of the audit's event stream. For example, this graph represents the audit event stream from the previous slide. So researchers have demonstrated that provenance-based intrusion detection systems, or PROV-IDS, are able to consistently detect attack behavior. In the example on the screen, we can see that the attack on the left-hand side features different system entities and is defined by a different graph structure, which can be leveraged by PROV-IDS to delineate normal and anomalous behavior. However, what is not clear, though, is how these systems react when presented with an adversary that utilizes mimicry attack strategies in the form of adding additional benign behaviors alongside the attack. So in our paper, we evaluate 5 state-of-the-art provenance intrusion detection systems. We introduce 3 mimicry attack gadgets that an adversary can utilize to evade detection, and show in our evaluation that our attacks were able to achieve 100% evasion against all 5 systems. The key finding from our paper is that currently, PROV-IDS are just as susceptible to evasion as prior HIDS technologies. For the brevity of this presentation, I'm just going to focus on 2 of the systems we evaluated in the paper. Going forth, I will provide a brief description of each system, some observations we made about the system, and how our attack gadgets exploit the system's weaknesses. So Unicorn is a PROV-IDS that summarizes system activity using the nodes neighborhood within the provenance graph. Specifically, given a provenance graph, Unicorn selects the local neighborhood around each node. For example, the local neighborhood around P1 forms the following substructure. Unicorn represents with the histogram of substructures and includes temporal information of provenance graphs by generating a snapshot as the graph grows. For example, we can see that 3 histograms formed here map to the 3 different timestamps in the provenance graph. To compare provenance graphs of different sizes, Unicorn normalizes the counts of unique substructures within each histogram. Unicorn then embeds each histogram into a d-dimensional vector using a novel embedding algorithm called histosketch. It then compares these embeddings against a model of normal behavior learned during training. If any of the d-dimensional embeddings fall outside a cluster, Unicorn raises a flag. So here we see an overview of Unicorn. By utilizing the node's neighborhood, each node's neighborhood, Unicorn takes in provenance graph rich in information and converts it into a d-dimensional embedding. By doing so, Unicorn loses key information that allows for the attacker to evade detection. I will now discuss one of the 3 attack gadgets we introduced in the paper, abusing distributional graph encoding. The first insight we see is that to compare against provenance graph of different sizes, Unicorn normalizes the counts of each substructure in the histogram. This means that each substructure count inherently depends on the counts of the substructures around it. An attacker with control of their process space could arbitrarily reduce the weight of their attack substructures by upsampling the number of benign substructures that appear within the graph. What this looks like in practice is the following. Given that the attack starts at timestamp 4, we can see that the attack substructure carries a weight of 0.03. However, if the attacker, as part of their attack strategy, inserted benign substructures alongside their malicious behavior, we can see that the weight of the attack substructures is reduced from 0.03 to 0.02. By iteratively increasing the number of benign substructures that are added to the provenance graph, the attacker can reduce the weight of attack substructures until they no longer have an effect over the resulting embedding. The second system I will now present is Prov Detector. Prov Detector deconstructs and represents the graph by the individual paths that exist within it. For example, one possible path could start from P1, go to P3, and end at F3. Similar to Unicorn, Prov Detector first collects the set of substructures from the provenance graph. However, unlike Unicorn, Prov Detector assigns a rarity score to each substructure instead of normalizing the substructure counts. The rarity score represents the probability of the path occurring in the training dataset. The larger the rarity score, the less likely the path will occur. The rarity score is calculated using a frequency table generated over the training dataset. This frequency table lists the frequency of each unique edge in the training dataset. The rarity score is the path of the path is then the summation over all the edge frequencies that make it up. To compare graphs of different sizes, Prov Detector selects the top n rarest paths from the given provenance graph. In our example, n is equal to 2. And we can see that the attack substructure is correctly selected. Prov Detector embeds these paths into a separate d-dimensional vector and compares each vector against a model it learned during training. If any of the paths fall outside of a cluster, it creates an alert. Here, once again, we present an overview of Prov Detector. We can see that the provenance graph rich information is once again reduced down to a d-dimensional vector, losing key information. So we will now introduce another attack gadget from our paper, abusing downsampled graph encodings. The first insight we notice from Prov Detector is that it selects the top n rarest paths from the provenance graph. Because provenance graphs represent system-level activity and systems are often non-deterministic, there exists a lot of variation between provenance graphs. As a result, even within the benign training data, there occur paths with large rarity scores. So an attacker looking to evade detection can add these additional benign behaviors that carry high rarity scores such that the attack substructures are pushed down and no longer used to represent the graph. Here's what it looks like in practice. Take 2 provenance graphs, similar to each other, except for the attacker's behavior. In the provenance graph, in the top provenance graph, we see that the attack substructure is correctly selected to represent the provenance graph. However, in the bottom provenance graph, alongside the attacker also includes a benign substructure. This, in turn, adds another substructure to the set of substructures Prov detector extracts, one with the high rarity score, such that Prov detector selects that substructure instead of the attack substructure that was supposed to be correctly selected. This allows for the attack to no longer be part of the selected paths and represent the provenance graph, allowing for the adversary to evade detection. To show the effectiveness of each gadget, I will now present some experimental results. In our paper, we evaluated against two different data sets, the StreamSpot dataset and the DARPA Transparent Compute 3 dataset. For this presentation, I will focus on the StreamSpot dataset, which contains 100 separate attack graphs. So in this first graph, we see our evasion results against Unicorn. In the x-axis, we see the number of edges added by the attacker alongside their attack to the provenance graph. The y-axis shows the distance of the provenance graph from the nearest cluster, and the purple line is the average distance from the cluster centroid for each cluster in the model learned by Unicorn on the training dataset. We can see that as more edges are added into the graph, all 100 attack graphs get closer and closer to the cluster boundary until at 40,000 edges added, all 100 attack graphs fully evade detection. Now, it may seem like inserting 40,000 edges to the attack is a large amount of perturbation and could be easily detected by a simple statistical test. However, if we compare the number of edges added to the size of an average benign graph, we see that the perturbations made by the attacker represent a small fraction. In fact, we show in our paper that utilizing statistical tests to detect these perturbations is non-trivial. We see a similar pattern for Prov detector. Again, the x-axis represents the edges being added by the attacker alongside their attack. The y-axis represents the distance to the decision boundary, and the purple line represents the average distance to the decision boundary. As more edges are added, our attack gets closer to evading detection against Prov detector. Until at 9,000 edges, it is successful. Unlike Unicorn, however, the attack against Prov detector is different in that it utilizes less edges and displays a nice step function towards evasion. This is in part because Prov detector downsamples the graph, meaning that the attacker needs to iteratively add a benign path with a high rarity score at each timestamp until evasion occurs. We also provide some evaluation results for the other three Prov IDSs we evaluated against. So this is a result on StreamSpot, Pagoda, and Sigil. For all three systems, we can see the same pattern as before, where as more edges are added into the provenance graph by the attacker, the provenance graph becomes less and less malicious to the IDS. Some other experiments we conduct in our paper include a live experiment. The live experiment is able to show two things about our attack strategy. One, that an attacker with limited knowledge of the benign behavior of the victim system can still successfully evade detection. And two, the graph transformations that we made in the feature space can successfully be transferred over to the problem space. We also compare against recent work from the adversarial machine learning community. Because many of the current provenance intrusion detection systems do not use gradients when learning on provenance graphs, most current adversarial work against graph learning algorithms is not relevant. However, black box attacks, which do not make any assumptions about the underlying model, could be applied to a problem space. We use the reinforcement learning-based adversarial attack to compare a method against. However, unfortunately, reinforcement learning-based methods carry a large amount of memory and computational cost. As a result, the reinforcement learning-based method was not able to scale up to the number of edges required to successfully evade detection. In our paper, we have many more experiments, such as statistical tests and results on other data sets. We encourage interested listeners to go read our paper. So the attack gadgets we've presented so far in this paper were based on observations we made about the Prov IDSs we evaluated against. The goal of this paper was to understand the limitations of the current landscape of Provenance intrusion detection work and provide some insights onto why these systems are failing. Something that out-of-the-box machine learning could not provide us, even if we could get an adversarial attack to work. And however, at this point, there does not exist current work in adversarial machine learning that can be applied to provenance graphs that creates enough perturbation that allows for attackers to evade detection. So we think that in future work could take some of the insights that we've created in this paper to generate a new adversarial attack that's able to efficiently scale up to the number of perturbations required to evade detection. In conclusion, we show that provenance intrusion detection systems, by applying out-of-the-box machine learning techniques, lose critical information from provenance graphs. Moreover, because all these systems do whole graph classification, they're required to consider the entire activity on the system, which means that the classification of these systems are inherently dependent on the attacker's behaviors. As a result, the attacker can introduce additional benign behaviors alongside their attacks, such that the anomalousness of their actions are masked. Thank you for listening to my presentation. I'm open to any questions you might have. If you're interested in this talk, you can scan the left barcode to access the code repo of this paper, and you can scan the right barcode to get in contact with me. Thank you.
Thanks, Akul. We have plenty of time for questions here if anyone wants to ask any questions. If you do have a question, feel free to unmute yourself. So I guess while people are thinking, I'll just ask kind of a high level. So now that you've seen that mimicry attacks are applicable to provenance intrusion detection, does your group have any insights or suggestions or possible directions towards addressing this kind of mimicry?
Yeah, it's a good question. I think like a lot of the work currently done in provenance intrusion detection systems has been whole graph classification. So given a graph, can you detect if anomalous activities occurring within that graph? But this requires you to summarize this large graph into some kind of embedding that you can then compare against. And this is a little bit brittle. So one thing that going forward we think should be more of a focus for the community is to look at lower level classification of subgraphs, classification of nodes, classification of edges, because these are a lot harder to perturb against than the entire graph as a whole. Those are some of the key insights that we created. We think that like this focus would definitely like a change in focus would definitely allow for the systems to be more resilient. But like some of the other things that our group is now focusing on is not just applying out of the box machine learning, but integrating how system analysts analyze provenance graphs. A lot of the models currently are just taking, a deep neural network and then throwing it like a provenance graph. And these neural networks make assumptions that aren't really akin to what provenance graphs, the environment that provenance graphs live in. So can we adjust and create new techniques in, machine learning that are specific towards provenance graphs themselves?
Yeah, it's interesting because so mimicry pops up all over the place, and in the domain of document malware analysis, something that people very quickly figured out was if you're an attacker and you make a malicious PDF document and you know that someone's going to try to use a machine learning or statistical approach to detecting whether this document is malware or not, the most trivial kind of attack you could do is you take your malicious document, you grab one or two benign documents, and then you simply just concatenate them onto your document. And basically, the benign features of the PDFs you've concatenated outweigh the malicious features of your original document, and you evade the detector that way. And I know in the space of malware analysis, the way, at least the short-term way that they try to address that, is they change the way that the models work. So that way features can only contribute to a maliciousness score and can't subtract from it. So there were limitations with it, but at least that got rid of the kind of the traditional, or like the low-hanging fruit of like padding or padding to get around a model. And then where I think that line of reasoning kind of hit a dead end is that just because of like Turing completeness, there's an infinite number of ways to achieve the same outcome. So you can potentially, with enough time, always find some functionally equivalent alternative sequence of API calls to achieve the same effect. And that's why Mimicry has kind of stuck around since like the beginning of computer science, or I should say since the beginning of cybersecurity. So yeah, it's interesting.
Yeah. It's interesting you say that because in Provenance graphs, I mean, we're looking at a certain representation of audit streams. There's also a whole host of work that still evaluates on audit streams in this sequential manner, similar to the force IDS. And a lot of the work is like, let's throw a transformer because this is like a sentence, so we can like kind of use it as text. But if you look at like how transformers are constructed, they also utilize a window size. So transformers don't like operate in this infinite window size. They have some kind of limitation. And so even though like you could potentially get some really great, representations of audit logs, because they use some kind of window, the mimicry attacks that, Wagner and Soto introduced could probably still be applicable against these systems just because they have this, window size that they have to deal with. And it's not clear, like I said, it's not clear that you can just throw, transformers and solve the problem. Like there has to be something unique about what we do from like as system analysts. We know how system analysts analyze these systems. We have to like utilize those techniques and like integrate them into the machine learning to provide better results, because it just like throwing something at it won't help at all.
Yeah, it's interesting because so in the old school anomaly detection, you would look at these linear system call sequences, and then you could just pad them as an attacker to evade. And then the way that people try to save that line of research is they then started applying program analysis to basically causally link system calls together. So that way they can figure out, these 5 system calls in the middle here don't actually contribute to the first or the last system call. And that's kind of a way of getting rid of the obvious padding in the sequence. And in a lot of ways, data provenance is kind of the next evolution of that. It's just rather than drawing the causal links between system calls within one program, now you're drawing the causal links between subjects and objects across the whole system.
Right.
Yeah, it's interesting to see the mimicry attack continue to persist as we kind of come up with more and more techniques for doing this this modeling of the system.
Yeah.
And I'm not really sure what the answer is, because ultimately this boils down to the like vanishing horizon problem. And as long as you have a finite window or finite memory, there's always going to be some bound on how much prior events you can take into consideration when making a decision.
Right.
Yeah, it's interesting. It's also kind of interesting to me that the reinforcement learning, at least kind of the existing techniques, struggle to find the attacks, because the reinforcement learning systems also have a limited memory. So on the one hand, your mimicry works because you can attack the limited memory of the defense. But on the other hand, automating the attack is also hard because of its limited memory.
And I mean, one thing to note with the reinforcement learning approach, these systems are built for like social networks where like you want to, change the classification of the social network or whatever. And they're built to be optimal. So there's a couple of things. They're built to be optimal in a social network, meaning that there's a lot more restrictions on what edges you can add. Less restrictions, right? You can kind of, in a social network, you can kind of be friends with anyone, and there's no direction in the friendship. But in Provenance graphs, because we're modeling systems and there are interactions between system entities, you can't have like interaction between a file and a file. That doesn't make sense. Like a file can't read another file, right? And so there's like a lot of these restrictions on how the problem space is a lot more constrained. Like you have to have certain edges inserted. And so these systems, like this reinforcement learning algorithm was built so that it could just add like one or two edges that optimally change classification. But in our problem, that one or two edges that may change classification is not possible. And often, I mean, that's being said, like the way we ran the experiments, we allowed for the attacker to change anything. Like we allowed for unrealistic edges and it still didn't work. But even if we like hadn't allowed for unrealistic edges, like it's just the problem space is so much different from like social networks that like these reinforcement learning algorithms do not work very well. That being said, like, one thing that I believe is probably like a solution or a way to get around this is to think of the problem not from a graph perspective, from the feature space, but from the problem space, meaning that like an attacker. So we made these transformations both on the graph level, and then we did a live experiment to show that it could work with an attacker. But realistically, all these attacks should be working as like an attacker. The attacker can only do certain things on the system. They could control the system calls, but really they're like clicking on the windows, they're exploring the internet, they're doing stuff like that. And so being able to simulate that and like embedding that information into the reinforcement learning algorithm would be a potential way to get around that, because now instead of adding a single edge to the graph, you're adding a behavior, which is a subgraph to the graph. And so you're adding a lot more edges at each time step, and that's allowing you to cut down on the cost of computation and memory. But just a different, like you said, like a different way of viewing it, right? Because these models were created for social networks, where it's like, let me just add an edge, let me add a connection between two people. But like in security, there's no such thing. And like, so if we like rethink the problem as like, okay, let's add behavior, then we start to see some parallels, but it's not exactly the same either. And so like coming up with something that can kind of adapt pretty well into this space of like, let's try to identify a reinforcement learning algorithm that can add behaviors that allow for the attacker to evade detection. Now that's interesting. And like, I think, something that's pretty plausible to do.
Yeah, I'd have to imagine that there's some way to essentially hill climb your way to an attack.
Right.
So even if you can't in one step go from detected to undetected, if assuming a white box model, or at least you have as a feedback the score, being able to hopefully at least hill climb.
Right.
Now, whether hill climbing causes you to get stuck in a local optima where you just can't quite get far enough to be undetected, is a question in itself. But
right.
Yeah.
So I know, sorry, go ahead. Go ahead.
I was just going to interject that Amareza has a question, which is it possible for the topology of the graph to be changed as time goes on, or do we have switching to another topology?
Right. So that's a good question. The short answer is no. And there's a couple of reasons for this. It depends on how you're representing the graph. Technically, Provenance graphs should be DAGs, meaning that there shouldn't be any loops or anything. However, like that's not how it's done in practice because of space requirements. That being said, like the topology of the graph, you can only add edges. You can never delete edges from the graph. You know, once the system event has occurred, that it's occurred. You know, you can't, unless you're making you don't have the assumption that the system logs are protected. So like on a lot of the work in this space, the common assumption is that your system logs are protected and an attacker can't, modify that, because an attacker could start to modify your logs. Well, no intrusion detection system will be able to pick it up because they could just delete their, behavior arbitrarily. So, bar that, there's not really a good way to delete edges in the graph. There's only you can only add edges as the graphics gets bigger and bigger. So yes, the topology of the graph wouldn't change in that sense. It would only get bigger. Yeah. I don't know if that answers the question, but
yeah. Feel free to okay. Amareza says thank you. So yeah, I think that answers his question. So refresh my memory from data provenance. How do you ensure that the provenance graph is a DAG? Because, for example, do you model, for example, memory writing or pipes between processes? Because what if one process has a pipe into another process and then that one has a pipe back? What happens in that case?
Right. So it's not as complicated as you might think. There might be some really sophisticated solutions. The community, what it's thought of is we'll just version the nodes. So
okay.
if you have, so we'll just create more nodes to represent the different iterations of the same object.
I see.
And so then that way you can DAG it. But then you get this explosion in the number of nodes in the graph,
right.
and your size of the graphs gets huge. And so it's not done in practice. You can't really go about doing that. And if you are correctly modeling your edges, these systems, for example, Unicorn does model the timing of the edges. And so if you start associating time with each edge, that can also take into account the different, it's not a DAG anymore, but you can always take into account the information flow. You can't have information flowing back into the past, right? That wouldn't make any sense.
Yeah, I guess in the worst case, even if the graph itself is a DAG, when you sample the graph to build your samples for the machine learning model, you could make it a DAG at that point by just not traversing backward edges.
Right.
Okay. Any other questions from the audience? All right. Well, that's all the questions and comments that I have. Pretty quick talk, but definitely very interesting work. And I would strongly encourage people to check out data provenance if this is an area you're not familiar with, because it's a pretty active area and quickly growing. And there's a lot of interesting stuff going on here, both from Adam's group and some groups at Purdue. And I've also done a little bit of collaboration with Adam, so definitely check it out. Real quick, once again, thank you, Akul, for taking the time to talk to us, and please give my regards to Adam Bates. This is the last presentation in our speaker series for the semester, so once again, just thank you for everyone who's been attending these talks on Fridays. And also special thanks to Julia and Nicole, who have been a great help in helping organize and put on these events. And I believe that's all I've got. So have a good weekend, everyone, and see you around.
Thank you.